Hey everybody, welcome back to Bayesian Stats. This is about where we stopped last time, and I just want to let you know that I made a couple of small edits to the code that I posted and to the notes. So if you are saving these somewhere, now's a good time to re-download both the code and the notes. Mostly around how we extract information criteria from models, which is what we're talking about today. We're talking about information criteria. And as a warning, this is a fairly philosophical lecture. This is a fairly philosophical topic. Unlike the R-squared, information criteria, I feel, are quite philosophical. They're near and dear to my heart. One of my favorite statistics papers is on information criteria by Burnham and Anderson, 2004. Look it up. You're not required to, but it's a good read anyway. Anyway, when we get to evaluate models, what we talked about last time around the R-squared is probably the worst way to compare models. As I said last time, it's probably the R-squared or its close brother, the mean squared error, mean squared prediction error. These are closely related, and they are probably the worst way to compare models because these overfit. They overfit. If you are trying to fit your data to maximize your R-squared, you'll be picking up all kinds of false signal, which should be left as noise. A better way that is used very, very often is a type of metric, which is adjusted within sample accuracy. We take something that is a raw measure of goodness of fit, and then we add a penalty term. We penalize ourselves because we are fitting the model and then evaluating the model on exactly the same set of data. But we're interested in making inference on the population from which our data came from. And so we're going to penalize ourselves for being overly optimistic. And so out comes information criteria. So we correct our within sample performance bias, applying the penalty term. This is very widely used. So really this lecture is about understanding what we're actually estimating with information criteria. We will go through some frequentist and some Bayesian information criteria, and with the caveat that I cannot possibly cover all information criteria. There's a ton of information criteria. There's also some rules of thumb that are probably applicable to some fields. So I'll be covering ones that are sort of general purpose. And with again, the caveat that there are fields that prefer one type of criteria over the other. So these information criteria are tools for general prediction problems when we want to pick a model well suited for prediction. Now I say general because if you have a specific prediction problem, then cross-validation is probably a better way to go. So if it's a prediction that you have to do over and over and over again, then one sensible thing to do will be to develop a model, take a data set, then randomly select about 70 to 80% of the data, make a model, and then evaluate the fit of that model on the remaining 30 or 20%. So this is unseen by the model. So this nicely represents the task of modeling data that has not yet been seen. This task is being approximated by information criteria and completely sort of overlooked by within sample accuracy criteria like R-squared. So, if the question is, well, why don't we do cross-validation all the time? There are fields that do cross-validation all the time. However, not every field can collect enough data to justify leaving out and not using 20 or 30%. Also, which 20% do we leave out? Do we randomly select 80% just once? Or do we run something like, 10 times this exercise where 10 times we select a random 20%, and then we put it aside, make a model on the remaining 80%, and then evaluate on the 20% that is unseen by the model. And then we repeat this 10 times and come up with some kind of an average. That is kind of how we do it. But you should be kind of listening, well, that takes quite a bit of time. Isn't it easier just to type AIC model? It is. But if you have a specific prediction task, the cross-validation technique is going to give you the best result. Of course, it's also time consuming. If you're doing this task 10 times, that is 10 times the computing that you have to do, 10 times the wait time. If you have a data set of 1 million rows, then you have to fit your model to 800,000 rows 10 times, as opposed to typing AIC model. So for all those reasons, AIC are far more widely used, at least in the fields I deal with, than cross-validation. Now I know some of you are more familiar with computer science, where cross-validation is the name of the game. So again, I have to make a lot of caveats because I'm talking about sort of a general information criteria use that is commonly applied in public health, social sciences, which are the fields, education, fields I am most familiar with. Computer science, I am not as familiar with. So let's talk about some overarching principles of what the information criteria are trying to do. As I said, they're trying to approximate a model's out-of-sample predictive performance. The cross-validation approach is actually doing the out-of-sample prediction. Information criteria is an approximation. All information criteria are an approximation. What this really means is all have flaws. All have flaws. Every information criteria out there has flaws. Cross-validation also has flaws. What if you only do it once and you just get lucky or very unlucky, and you select a model that is not good for unseen data? All information criteria has flaws. Our author, McElreath, thinks that every model, and I agree with him, every model represents a complex hypothesis. If you're saying I have 3 competing models. One is that height is a function of weight. The other one is that height is a function of weight and the person's sex, and height is a quadratic function of weight and sex. Each one of those models represent different hypotheses. Does the effect of weight on height remain linear for the foreseeable range of values, or does it become nonlinear? So if our quadratic model is selected, then that hypothesis gains traction. Of course, this is an important result. Best model is not necessarily unique. We can come up with, especially in the age of big data, we can come up with 2 models that have near equivalent information criteria, near equivalent log likelihoods, but with a very different set of covariates. So how do we know which model is best? Well, it's whatever the scientific question that we're trying to answer. I think, as you might know, I am against sort of a blind, stepwise model selection, unless that's really all you're trying to do. If you're trying to understand the data, then sort of blindly fitting subsets of available covariates is not a good approach, because you can come up with a whole set of models with very, very similar information criteria and wildly different covariates, just based on how covariates are correlated. So, remember I said this is a philosophical lecture. The other few overarching principles, some of you may have heard of Occam's razor. A little trivia, there is actually multiple ways of spelling William of Ockham, his name. So you will see this spelling that I have up on the screen. Sometime you will see this spelling. Here is the Occam's razor sort of statement in Latin. Here it is in English. Plurality should not be posited without necessity. In this case, plurality is in the parameters. in our sense. So what Mr. William of Ockham, this good-looking fellow with the haircut right there, what he is saying is we shouldn't estimate more things if we can get away with estimating less things. By the way, a razor is that, sort of to shave off unreasonable outcomes. So we use Occam's razor to shave away models that have too many parameters, and we're only left with the models with just the right number of parameters. How many parameters do we need? How many variables or parameters do we need? Well, if we have too few, then we have low variance, but we're going to have biased predictions. Right? So the issue is that we get biased predictions, but we do end up with low variance. We have low variance because we have few unknowns. Few unknowns, less uncertainty, low variance. But we're missing the signal. We have biased predictions. If we have too many variables, we haven't shaved off enough with our Occam's razor. We have too many variables. Then we're going to make unbiased predictions, but they're going to be unstable / uncertain. We'll be carrying too many unknowns that interact in unknown ways. And so if we have too many unknowns, we have high variance. Low bias, yes, high variance. So again, I keep coming back to this, is what is the scientific intent of fitting this model? And actually, this brings this young fella into the picture. Dr. Box passed away somewhat recently. He is perhaps most well known for founding the Department of Statistics at UW-Madison and saying something along the lines of all models are wrong, some are useful. So I believe Dr. Box would back me up when I'm asking, what is the purpose of us fitting a particular regression model at hand? Is it to make a high variance but low bias prediction? If that's the case, don't worry about information criteria. Turn off this lecture because we're going to be focusing on what is the optimal number of parameters such that we have reduced the bias but not introduced too many unknowns. I think these two things were not said by Dr. Box, but I think that all models are wrong, some are useful, points to the fact that the ultimate truth is fundamentally unknowable. And what we're doing with computers is we're just fitting different mathematical approximations of an infinitely complex reality. We can't possibly account for all influences on every single process, with few exceptions. I keep coming back to exceptions. Unless you're dealing with some kind of a chemical process where every single input and output is known. At that point, you don't even need statistics that much, right? All error is measurement error. For most interesting problems, your statistical models can't possibly account for every input and output. This is probably true for almost every problem in public health, almost every problem in social sciences, almost every problem in education. Those are the three I'm most familiar with. So our models are then tools. They're tools for us to answer certain questions, right? They're tools for us to rank hypotheses. Right? Models are tools to rank hypotheses. Some are going to be more true than others. All right, that just doesn't want to, all right. And there is the word, hypotheses. Some hypotheses are going to be more true than others. Ranking our models based on information criteria allows us to say, hey, this model is most plausible for this data set. This model is least plausible for the data set. All of them are wrong, but maybe the one that we rank as best according to information criteria has the greatest chance of being useful. So to get where we're going, which is Bayesian information criteria, I have to start with frequentist information criteria. Why? Well, first of all, they came first. Second of all, a lot of Bayesian information criteria are strongly based on frequentist information criteria. And when you leave me, you're not guaranteed to always use Bayesian analysis. I don't always use Bayesian analysis when I do, when I work with someone, when I collaborate with someone. So perhaps the most used and also the most misused information criteria is the Akaike information criteria. That good-looking guy in the top right of the screen is Hiratsugu Akaike. He has his 1974 paper is the 73rd most cited paper of all time. A little bit of trivia: the most cited paper of all time has to do with proteins. I hear proteins are super important. AIC is also pretty important, I think, for being a tool to rank statistical models. Being the 73rd most cited of all time is pretty darn impressive. So what is it? What is that number that pops out when you say AIC of the model? What is that measuring? It is an estimate. That's a keyword. It's an estimate. Remember, information criteria are trying to approximate some type of a cross-validation error of the distance, in quotations because it's not a true distance, between full reality, I told you about that this lecture was going to be philosophical, and the specified model. You hopefully know what you have specified. So of all of those statements, perhaps we can disregard estimate and disregard specified model. What full reality means, is somewhat up for debate, but I will mention that the distance, this is based on the Kullback, oh, I'm going to misspell this, Kullback-Leibler. And the Kullback-Leibler is not a distance, it's a divergence. A distance is the same whether you go from this end to that end. A divergence, you have to go, it's directional. The AIC is directional. However, that all of these are details that we tend to overlook when we use the AIC. If we think of it as a distance, then it's pretty clear that we want smaller values. We want to minimize the distance between full reality and the model. That's why we select models with a small AIC. This statement is also true, again, and remember, AIC is just an approximation of basically leave one out cross-validation error. And you can show that if you rank a bunch of models based on the AIC, that is asymptotically, again, just to be clear, it says n approaches infinity. Do we ever get to see that world? No, we do not get to see that world, but sometimes we get pretty close. Ranking models based on AIC is asymptotically equivalent to ranking them based on leave one out, leave one observation out, build a model on the remaining observations, predict that observation, and leave one observation out at a time, average your error, and that is the leave one out cross-validation error. So we want to minimize the distance, we want to minimize cross-validation error. All of that indicates that we're going to select models with a smaller value of the AIC. Here's a formula. By the way, this term, the first term, is sometimes called the deviance. It's -2 times the log likelihood. Why -2? I think it's for historical reasons, as far as I understand it. Then this 2K is a penalty term. So it is 2 times the number of estimated parameters. The idea is we want to account for how much resources we used to get however close we got to this full reality. So I said it's the most used and the most misused because it is a poor estimate of that distance between full reality and the model if the number of parameters is large relative to the amount of data. I think this word relative is super important because the number of parameters is large. If you stop reading that line there, then it could be well, I don't think that 10 parameters is large. But if you have 10 parameters and you are using a data set of size 30 to estimate 10 unknowns, that is not a ton of data relative to the amount of parameters you're trying to estimate. Rule of thumb is about 30, right? We want to have about 30 observations per parameter. That's a rule of thumb. So if you have the case where you have 100 observations and even 5 parameters, that does not quite meet that rule of thumb. So AIC is a poor estimate of that distance when the number of parameters is large relative to the amount of data. This also says that, in the world of big data, if our models grow in complexity at the same speed as the data, then we're also really can't be using the AIC. One of the more confusing results is that the classic AIC has been shown to quote unquote overfit. That is, select a model that is too complex in simulation studies. I hear your question. Isn't this exactly what it's trying to avoid doing? And the answer is yes. But modern analyses, we tend to have, our gluttonous with respect to the parameters and often fit models that are, again, too complex for the amount of data that we have. So in those cases, AIC tends to select models that are too large, too complex, overfits. It also is unclear somewhat about how to count parameters in multi-level models. I'll sort of leave it right there for now. We'll be covering multi-level models at the very, very end of the course. And I might come back to this slide then. My other comment, I've seen a couple of R packages that basically allow you to change the 2 in the 2K to some other number. They call it something like the AIC3 or the AIC6. And that number is not an arbitrary number that Dr. Akaike came up with on the train. He came up with AIC on the train, apparently. But that number 2 is not an arbitrary number because, again, we're estimating that distance between reality and the model. So that 2 is a part of that distance. So if you are trying to change that to a different number, you certainly can. The stats police won't break down the door and get you. But you have to be asking the question, what are you really estimating then? Because it no longer is the distance between reality and the model. So that was a lot said about the good old AIC. Thankfully, we have a corrected version of the AIC called the AIC little c, corrected AIC. It promises to select a model with a minimum distance to full reality for a given sample size. So it implicitly, but really explicitly, accounts for your sample size. The classic AIC does not account for your sample size. Notice that we are looking very similar to the original AIC right through there. And then we apply a correction term to that penalty. That correction term, to see what's going on, take the numerator, I'm gonna write it right over here. Take the numerator and the denominator of that term and divide it by n. You take the numerator and the denominator and divide it by 10. You get 1 over 1 minus k minus 1 over n. So you see that as n approaches infinity, right? As n approaches infinity, this term goes to infinity. As that term goes to infinity, then k minus 1 over infinity, oh, erase too much. K minus 1 over infinity goes to 0. And then the entire correction term simply approaches 1. And then we collapse back to the classic AIC. So if our sample size is large compared to the number of parameters you're trying to estimate, the corrected AIC will be very, very, very similar to the classic AIC. Bingo. This really should be the default information criteria for all frequentist analyses. Now, I think this is not the case for a few reasons. One is there's not a ton of packages that output this automatically, at least that I'm familiar with. That could be my own limitation. I'm aware of one. It could be that the name of the package is kind of long. It could be that if you're trying to code this by hand, it's longer to code. It could be that a lot of people are simply taught that AIC is best. Just look at the AIC, when we really don't understand the limitations of the AIC. So if you're gonna look for a default, the corrected AIC really should be the default, in my view, when you were doing frequentist analysis. Now, I will be destroyed if I didn't mention the BIC, or the Schwartz information criteria by Gideon Schwartz. By the way, I've been looking for a picture of Dr. Gideon Schwartz forever, and I'm still not able to find a picture. I'm able to find a lot of people named Schwartz, but I'm not going to put up a picture of a person unless I'm pretty certain it's Gideon Schwartz. So sometimes it's called the BIC. I've seen it called the SBIC. I've seen it called the SIC, which makes it particularly confusing what information criteria people are talking about. The penalty term of the BIC, interestingly, depends on N, and it increases with N. So as you obtain more information, you penalize yourself more and more. I always found this sort of odd. Why would you penalize yourself for having more information? That's a strange result to me. What the BIC promises to do is, if the true model, that ultimate truth, is among the set of models that you are considering, there's a lot of ifs there, then it promises to select it with probability 1 as n approaches infinity. Well, that's a tough set of criteria for me personally. Again, I warned you this is going to be a philosophical lecture. First of all, we live in a world where we're always far from n equals infinity. Second of all, can we agree that there is one ultimate true model? For example, my postdoctoral advisor thought this was a ludicrous statement. Some people think, no, I really think the true model is among these 5 I'm considering. My thought is this. In several simulation studies, the AIC frequently overfits, that is, it selects the model that is too complex. The BIC often overpenalizes because it has sample size as part of its penalty term. So because it overpenalizes, it underfits. So it selects a model that doesn't fit well enough. So again, the AICc, the corrected AIC, falls into that sweet spot. The other thing that was shown, and this is out of the Burnham and Anderson paper, if you want to look it up, I'll write it on the screen. Burnham and Anderson, 2004, I believe. Works poorly when there are a lot of small to medium effects, which is true for a lot of different disciplines. In social sciences, the influence of any one covariate tends to be medium to small. And there is a lot of different covariates. In political science, that's the case. I'm not going to argue what constitutes a medium and small effect, but I think, long story short, the BIC tends to underfit. The AIC tends to overfit. The corrected AIC tends to be the sweet spot. By the way, if you run a set of models, you select one with whatever information criteria, different information criteria usually will select different models. If for some reason every information criteria you use selects the same model, yes, you can go to sleep a happy person. But that so rarely happens, and then you're stuck having to explain to yourself, to your advisor, to the paper referees, why, which information criteria do you favor? My take: pick one, apply it to the model selection. That way, you at least don't have to compare why one information criteria selects one model versus the other. All right, a lot of talking. I warned you. Here is our good old heights example in a frequentist world where I am doing sort of kind of a ridiculous thing. I'm fitting up to a 6th degree polynomial, right? So it's weight alone. Here I use the word gender. Maybe the word sex is more appropriate for this data set. And a linear function of weight, quadratic, cubic, so on and so forth. Every model represents a separate hypothesis. Some of these models have more plausible hypotheses than others. Does gender matter after we account for weight? If we select model 2 over 1, then we say gender matters even when accounting for weight. Is the relationship between weight and height linear? If we select model 3 over model 2, we're saying that the hypothesis that the relationship between weight and height being linear is false. We have evidence to show that it's non-linear, so on and so forth. Here I apply both the AIC, the BIC, and the AICc, the corrected version of the AIC, to this model selection exercise. And look, lo and behold, we select 2 different models. Yes, we select model 6, if we're sort of blindly applying information criteria. Then model 6 minimizes the AIC and the corrected AIC, but model 4 minimizes the BIC. Remember, BIC tends to underfit, AIC tends to overfit, though in this case, the corrected version and AIC select exactly the same model. Now, the differences in the AIC, in whatever the information criteria, tell us how much evidence there is in favor of a particular model. How much evidence there is in favor of the model with the smaller information criteria. So, for example, there's a lot of evidence in favor of a 2nd order polynomial, because as we go from model 2 to 3, our information criteria drops by approximately 600 points. Now I say points because the units of the information criteria are uninterpretable. Differences are the units themselves are uninterpretable. So this drop of 600 points is huge. You notice that when I just add weight, the information criteria actually increases somewhat. Now, notice that between model 4 and model 7, so model 4 and 7 is once we get beyond a 2nd order polynomial, after we get beyond a quadratic, there's not much difference between these models. We go from a 3206 to a 3208, 3232 to a 3246. These are all very similar in order of magnitude. Yes, if you are really looking to minimize an information criteria, you're going to select the ones I have highlighted. But there is a lot of evidence because the information criteria, all 3, drop as we go from a linear to a quadratic. So we have a lot of evidence that the relationship between weight and height is nonlinear. So what do we do in the case that when we get different models selected? Apply science. I don't know the science of height and weight, but that's how I would settle this debate. If my collaborator came up to me and said, I have these 2 competing models, I would ask them, hey, let's go back to the science. What is the scientific question at hand? What does the prior literature say? And what do our 2 competing models say? The model that answers our scientific question at hand best, in the context of existing literature, that's the one we would pick. Continue to warn you about philosophy. Same, here I'm focusing on AICc. I'm reminding you that the units themselves of the information criteria and the log likelihood aren't interpretable, but the differences, the deltas, the differences in values are very much interpretable. In this particular R package sets the model with the lowest corrected AIC at 0, and looks like we're only different by about 2 points in these 2 models, 0.19 points for model 4. There is a rule of thumb out there that within approximately, again, it's a rule of thumb, 3 points, models are equivalent. So the long story short about this particular exercise is that models 4 through 7 are roughly equivalent, whereas these first 3 models are implausible. They are clearly have huge differences in corrected AIC from the other set of models. All right, now we're sort of ready to move into Bayesian information criteria. Now, again, things will get more complicated, and things will get more complicated because we need to be counting parameters, right? In the AIC, we get -2 times the log likelihood plus 2k. K is the number of parameters. It's easy to count parameters in a frequentist world because the parameters are constants. They don't have a variance. They don't have a standard deviation. They're constants, singular constants. But in a Bayesian world, we deal with something called effective parameters. Because in a Bayesian world, our parameters have posterior distributions that are a function of a likelihood and a prior. So intuitively, the number of effective parameters will depend on how strong your prior is. Strong priors imply that you have a lot of information before estimating the model. Strong priors say, I know exactly or pretty close the range of values in which this parameter falls. Weak priors, or even more weak, uninformative priors, say you have no information a priori about where a certain set of parameters falls. So strong priors will lead to fewer effective parameters. Weak priors will lead to more effective parameters. This is a nice and intuitive result. By the way, effective parameters is a measure of model complexity. Come back to William of Ockham. He was a friar. A model is more complex when we're trying to estimate more things. More formally, it's a number of unconstrained, unknown parameters. And that constrained bit comes into play right now. The other complexity of Bayesian information criteria is that we can be applying the same model to different data and could be coming up with a different set of effective parameters. Because of that constraint, we're trying to count unconstrained model parameters. So here's a very simple, it's a heuristic. So this is a deliberately oversimplified exercise that comes to us from Dr. Andrew Gelman from University of Columbia. So he says, all right, here is a simple likelihood, a normal distribution where we're just trying to estimate the mean. And the prior we set on that mean is a flat line bounded below at 0. That's the prior distribution we set on that mean. If we observe, if we fit that model to a data set where we have a teeny tiny average, where our average is already super close to 0, the lower bound of that prior will constrain our parameter. And by constraining the parameter, we are required to estimate fewer unknowns. If instead we observe a large mean, say 1,000, we are really far away. We are really far away from 0. So now in this case, our mu parameter is no longer constrained by the lower bound of the prior. And the number of effective parameters goes to 1. Why? Why 1? Well, I can count right there. That's the one. That's the one. That's the one we're trying to estimate. So the lesson to take away, in the Bayesian world, you could be fitting the same model to different data and come up with a different number of effective parameters. In a frequentist world, if you're fitting the same model to different data, you're going to be coming up with the same number of parameters. With the exception being multi-level models, but we technically don't know what those are yet. All right, another heuristic from Dr. Gelman. How strong a prior is should be considered with the scale of the data in mind. How strong a prior is should be considered with the scale of the data in mind. So here again, I'm fitting a normal distribution. Here is my prior. I come up with my hyperstandard deviation. This sigma measures the uncertainty in the data. This omega measures the uncertainty in the prior. Of course, low values of omega indicate strong priors. High values of omega indicate weak priors. The number of effective parameters that we're estimating, it can be approximated with this equation. And you can see that in the case of low omega squared relative to, and that's the key term, relative to sigma squared. If I'm assuming a high level of prior certainty relative to the uncertainty in my data, then I'm having a strong prior, and therefore I am I don't have to estimate as many uncertain parameters. If the opposite is true, if I'm assuming a fairly uninformative prior relative to the uncertainty in my data, if I have a weak prior, then I have to estimate a one effective parameter for this example. So the lesson to take away here is how strong a prior is can't be evaluated out of context. A normal 0-1 prior has to be compared to what are the units of measurement for your outcome variable. If the units of measurement are in the hundreds, that's a very strong prior. If the units of measurement are in the 0.001s, that's a very weak prior. This may have been intuitive, but perhaps it's good to sort of put it down on paper. All right. I know this was a very philosophical lecture, so let me sort of close it out for today with our first Bayesian information criterion. It's the first and perhaps the oldest, and perhaps the most widely used. The DIC stands for the Deviance Information Criteria. It was popularized by Sir David Spiegelhalter, who is holding those dice and smiling in that picture. He's a wonderful man. I had a chance to meet him when I was in Scotland for a conference. His paper was attacked ruthlessly for being ad hoc. It does tend to resemble quite a bit the classic AIC. And notice the classic AIC. It was attacked for suffering from the same issues as the AIC. And it was attacked for not being fully Bayesian because we still put in a point estimate. For example, the posterior mean. We evaluate the log likelihood at a point estimate. So it is sort of lost on us that we have a whole posterior distribution. So although this DIC is very, very widely used, better models are defined by smaller values of DIC. By the way, there is no longer a promise that this is a distance to the truth of any kind, but the authors of the original paper do say that better models are defined by smaller values of the DIC. The deviance information criteria does suffer from some issues. Of course, they want us to know that they too don't believe in any true model. But by using the deviance information criteria, we do assume that our posterior is approximately normal. Our posterior is approximately normal. So it somewhat fails if we have a lot of skewness in our posterior or our posterior is bimodal. Formally, I believe that this says that the posterior is well represented by the average. Remember that we just get a point estimate. We just get a point estimate in this term right here. So a posterior needs to be well represented by its average. That tends to be true for symmetric posteriors like I have in the middle there. The effective number of parameters that we have for example, in our book can actually be negative. This is the difference between negative 2 log likelihood at the average and the average negative 2 log likelihood. So this difference, which represents the number of effective parameters, can actually be negative. How do you interpret a negative effective parameters? I'm not sure. And I've already mentioned that the major criticism of the deviance information criteria is that it's not fully Bayesian. We end up relying on a single posterior point estimate to compute the DIC. Let me close out with a brief foray into R to show you the frustrating nature of effective parameters. So I'll actually be working with JAGs here. So this is going to be a Gibbs sampler. I'm still going to be working with the height example. And I'll be estimating the model where I have an intercept, the coefficient for weight, the coefficient for being male, and of course, the error standard deviation. So in this case, I can pretty easily count how many things I actually am estimating. I'm estimating 4 things. So let's see what happens as I play around with these priors. Remember, the effective parameters depend on how strong the prior is relative to the scale of the data, and the effective number of parameters will be affected if I am bounding the parameter by some bound, lower bound or upper bound. So these are the reasonable weakly informative priors that I had up in the last lecture. And if we run the model, all right, here are my estimates. Everything converged. These effective sample sizes look pretty decent. Maybe this is a little on the low side, but it's still well over 1,000, which is what we look for. Here is my estimate of the effective parameters. It is 4.4. I tried to estimate 4 things, and JAGS has returned 4.4 as the estimate of effective parameters. I tend to be happy with this estimate. It's intuitive. I can count the number of things I tried to estimate, and I can read off the screen that JAGS thinks I have 4 effective parameters. And by the way, there's the DIC. The DIC, that magnitude is meaningless. The units are not interpretable, but we do get the reminder that lower is better. And the DIC is the estimate of expected predicted error. Clearly, we want to make that as small as possible. So let's really mess up the priors. So in JAGS, remember that we're dealing with normal distributions that are parameterized in terms of precision, and not the variance. So when I say dnorm 145, 100, this is actually a really informative prior. Right? Because this is corresponding to a variance of 1 over 100. These two are pretty informative. And I am really messing up this exponential distribution as well. because this has a mean of 1/10 and a variance of 1/100. So these are quite informative priors. So let's see what they do to the effective number of parameters. The preview is it's not going to go in the direction we expect, but it's going to be a ridiculous estimate nonetheless. By specifying really informative priors in JAGs using the Gibbs sampler, it is outputting that, first of all, again, look, everything has converged. Everything has converged. All the effective sample sizes are looking good. Actually better than the other priors. But notice that JAGs thinks, although I tried to estimate 4 things, the effective number of parameters was 153.1. So if you were running this model and you try to specify priors and you just forgot that JAGs parameterizes everything in terms of the precision, and you ran the model like that, the first tip-off that something went wrong would be in this effective parameters number. No way are you estimating 153 things. It's just lying to you. And oftentimes, when you're running a Bayesian analysis, the first indication that you messed up the priors somehow is in this effective parameters statement. The DIC, again, that value is only comparable to what it was, but I'm not even going to compare it to the first model because I know something went wrong with my priors. This is nowhere close to the actual number of parameters, 1, 2, 3, 4, that I'm trying to estimate. So it is rare that I leave you with a frustrating note, but it's an important note nonetheless. We learned about frequentist information criteria. We learned the things that affect the effective number of parameters. And we learned that the effective number of parameters being super far away from the actual number of uncertain terms that you're trying to put into a model, that can be an indicator you messed up the priors. You messed them up. Go change them. Thanks, guys, for listening. This was a very philosophical lecture, a lot of talking at you. This is just the topic, so I appreciate you sticking with me. We're going to finish it up on Thursday. That is when I will assign the homework as well towards the end of the week. So thank you guys for your attention. I hope you do tune in. Have a good rest of the week.